My name is Christian Canals, and today we'll be going over key example variation problem 13.9 from chapter 13's homework. This one discusses orbital mechanics, and part A is asking us, or telling us, some comets are in highly elongated orbits that come very close to the sun at perihelion. The distance from one such comet to the center of the sun is 6.00 times 10 to the ninth power meters at perihelion, and 3.00 times 10 to the 12th power meters at aphelion. For this comet's orbit, find the semi-major axis. Okay, we were given the perihelion distance of, so that would be labeled as RP, and that would be 6.00 times 10 to the ninth power meters. And we're also given the aphelion, which I'm going to label as RA. So simply, the semi-major axis is just the average of both of these. So we're just going to set this up. It'd be A equals 6.00 times 10 to the ninth power m plus 3.00 times 10 to the 12th power m all over 2. That would equal out to be 3.006 times 10 to the 12th power meters over 2. And if you do the math on the calculator, that would equal out to be 1.503 times 10 to the 12th power. Since we are using sig figs, it would be 1.50 times 10 to the 12th power in meters. That is the semi-axis. Okay. That was simply part A. Now part B is asking us to find the eccentricity. So the eccentricity is simply the aphelion versus minus, so it's the aphelion minus the perihelion. What is it called? Perihelion. Wow. Okay. And that is going to be all over that, but just plus. And that's your eccentricity. Again, you're going to substitute the values. Since we do know what this one is from earlier question, I am just going to save us the time here and make it over that. So I know the last of this is going to be 3.006 times 10 to the 12 meters, but we're going to find out the other one. So it'll be 3.00 times 10 to the 12 meters minus 6.00 times 10 to the 9th meters. I'm going to just erase this for now. So we know this. We're going to do this. This would equal 2.994 times 10 to the 12 meters. And then we're going to put that all over 3.006 times 10 to the 12 meters. And that will give you approximately a concricity, or what is it called? Eccentricity of 0.996. Just using this formula that was stated in the book. And we already knew this one from earlier question. That one would be this. Well, no, it'd be from the earlier one. So you just plug in. Okay. Now we're going on to part C. Part C is pretty much just finding the period of the comet's orbit. It's saying, yep, it says express your answers in years. So for here, we are going to be using Kepler's third law, which is pretty much how you convert time from astronomical units. So this one right here is only if A is in astronomical units and T is in years. So we're just going to convert. So 1 AU would equal 1.496 times 10 to 11 power meters. And if you plugged it into the equation, it would be you're getting this from part A. This number is from part A. So you're just going to do this. Okay. Let me do the math real quick. It's saying it is about 10.03 AU. And now we're going to apply Kepler's law, which would be T equals square root of A cubed. So you will put A, which we just found. And then that will equal out to be 1009. Square root that. 31.8 years is your time. That was just using Kepler's third law. That is just a simple way to convert time into astronomical units. No. Astronomical units into time. You're probably wondering why T wasn't squared here. It's because T is 1, so 1 squared is just 1. Alright. Now we're going on to part D, which is saying the orbit of a certain asteroid around the sun has a period 7.85 years and eccentricity 0.250. Find the semi-major axis. Okay. For this one, we are given T equals 7.85 years. And we're going to use Kepler's third law to find out the astronomical units. So that would be A equals square root of T squared. Cube root of T squared, which would equal 3. Okay, so then you're going to convert to centimeters. So 3.94 times 1.496 times 10 to 11 power m would equal 5.89 times 10 to 11 power m. Okay, so here we use Kepler's law again. And then we just knew because at the time we just simply switched it back from T to A, which A would be the semi-axis. Okay. Now we're going on to part E. Part E is asking us to find the distance from the sun to the asteroid at perihelion and aphelion. I don't know how to say these words. And here answers in meters. So here are the formulas we're going to be using to find perihelion. It says here A minus 1 minus E. A times 1 minus E. And to find the aphelion, or whatever it's called, it would be that plus E. So we're given A. A would be the distance from the sun to the asteroid. So that would be 5.91 times 10 to 11 power m. And we're given E, 0.250. So we're just going to plug into these equations. 5.91 times 10 to 11. 1 minus 0.25 That would equal you 4.43 times 10 to 11 m. Then to find RA is going to be 5.91 times 10 to 11 power m, or whatever, minus times 1 minus 0.25, plus 25 this time. And then that would equal out to be 7.39 times 10 to 11 power m. That's how you find both the distances. And the problem has to sort it out by a comma. So here you are, comma, comma. So this would be RP. This would be RA. Okay, now we're going on to part F. One of the final parts. But we're going to be using a whole new planet. So the minor planet 3340 1998 VG44. It's just anything. That's like a Wi-Fi password. Makes exactly 2 orbits of the sun during the time that Neptune makes 3 orbits. The eccentricity of the orbit of the minor planet is 0.25, and the orbit radius of Neptune is 4.5 times 10 to the 12th power meters. Find the semi-major axis of this minor planet. Okay, we know that Neptune makes 3 orbits, and that VG44 makes 2. And we also are given AN, which is 4.5 times 10 to the 12th power meters. So now we're going to use the resonance ratio, which is pretty much TVG over TN squared equals 8VG over AN squared. So if you convert this into what we need, that'd be 2 over 3 squared. So that would equal 2. This is like what we're doing from before. 8VG over 4.5 times, let me clean that up, 12th power, which would equal 4 over 9 equals AVG Okay, I'm just gonna bring this down. I'm gonna bring that down. And then that would mean you gotta take the cube root of that. To get AVG by itself. And then you'd have to multiply 4 over 9 by 1/3 plus times this earlier. And that would leave you with 5.9 times 10 to the 12th power m. Okay. I know I got a little lost in translation. Pretty much your to find VG, you're gonna have to take the cube root of this one right here, because it is cubed. And the only reason it is cubed is because of this ratio here. Because we knew that it's just the resonance ratio is like that. So you're just gonna have to take the cube root of this side. And the main term we were trying to find is AVG. Because that would be the semi-major axis of VG. So that is how you found the semi-major axis. Now we're on to part G. Part G is asking us to find the distance between the sun and the minor planet at perihelion. Okay, so we know 5.9 times 10 to the 12th power meters. And we also know E equals 0.25. We know this. So now we're just going to apply it into the RP equation from earlier. And then that would be 5.9 times 12, 10 to the 12th power times 0.75. Only way we found this E is because we just did 1 minus 0.25. That's how you get that. And that would equal out to be 4.4 times 10 to the 12th power meters. Okay, now we're doing H. H is pretty much the same. We are given 7.41 times... No, actually, you know what? For part H, we are not given it. So, in 2017, astronomers discovered a planet orbiting the star HATS 43. The orbit of the planet around HATS 43 has a semi-major axis 7.41 times 10 to the 9th power meters. The eccentricity of 0.173, and then the period of 4.39 days. Find the distance between HATS 43 and the planet at its closest approach. Okay, perfect. This is talking about the star HATS. And it gives us all the numbers we really need. So again, we're going to find the perihelion, which would be what I'm writing right now. That would be the formula for perihelion. So you would get 7.41 times 10 to the 9th power times 1 minus 0.173. If you put this all in the calculator, you should get 6.13 times 10 to the 9th power m. And that would be your RP. So that would be the closest distance. Okay. For our final part is part I. Part I is asking us to find the mass of HATS 43. For comparison, the distance between Sun and Mercury and its as closest approach is 4.60, 10 to the 10th power meters, and the mass of the Sun is 1.99 times 10 to the 30th power kilograms. Okay. So with this one, we're going to use Newton's version of Kepler's third law. So that would be T squared equals 4 pi squared A cubed over GM, which we're going to rearrange to find M. So that would be M equals 4 pi squared A cubed GT squared. Okay, now we're going to convert time into seconds. So we're going to do T equals 4.39 days. That would be 4.39 times 864,000, which would leave you with about 379,296 seconds. And this is what we're given. We are given 7.41 times 10 to the 9th power m. We're given G, which is 6.674 10 to the 9th power n times m squared over kg. That's where we're given. And we're just going to plug all this in. So that'd be m equals 4 pi squared 7.41 times 10 to the 9th power cubed 6.674 times 10 to the negative 11th power times 30 squared, which would leave you with about 1.67 times 10 to 30 kg. That does measure to what we said earlier, or not eerily similar, but the numbers do make sense in the case of astronomical units and stuff. But that's going to be the final answer, and that's going to be the final work through of this evaluation problem. Pretty much it is just using stuff that we have learned from the textbook and just using formulas and numbers that we were given in the problems. So it's not too difficult. Thank you so much for watching, and hope to see you guys in another one.